66 million years ago, a rock roughly 10 kilometers wide slammed into what is now Mexico, and in one afternoon it ended the age of dinosaurs. That story, Chicxulub, the crater, the dust cloud, the extinction, is so well known by now that it barely needs explaining. It is the one impact event almost everyone agrees actually mattered. But here is a question that almost never gets asked. Was Chicxulub really the only time a rock from space reshaped the direction of life on Earth? The honest answer is that we do not really know, because Earth is terrible at keeping records of its own past. Weather erodes craters. Plate tectonics swallows them. Rivers, forests, and entire oceans rise and fall on top of the evidence. Give it a few 100 million years, and almost any impact scar gets wiped clean off the map. Today, across the whole planet, geologists have confirmed only a few dozen impact sites larger than 20 kilometers across, and almost all of them are younger than 650 million years. So if something big hit Earth further back than that, older than the dinosaurs, older than complex animals, older than almost anything we can dig up and date, how would we ever find out? The answer, it turns out, is to stop looking at Earth and start looking at the Moon instead. The Moon has no weather, no oceans, no plate tectonics. A crater punched into its surface 2 billion years ago looks almost exactly like it did the day it formed. That makes the Moon something like a fossil record for the entire inner solar system, a diary that Earth itself was never able to keep. And for the last few years, that diary has been hinting at something strange. A cluster of large lunar craters, including the 93-kilometer-wide Copernicus crater, all seem to date to roughly the same narrow window of time, around 800 million years ago. Samples brought back by the Apollo missions support this too. Tiny beads of impact glass, essentially droplets of rock that were flash melted by ancient collisions and then froze in place, keep clustering around that same 800 million year mark. Have you ever wondered what it would actually take to leave that kind of fingerprint on two worlds at once, without anyone on Earth ever knowing it happened? To answer that, you have to go looking in the one place scientists had not fully checked yet, the asteroid belt sitting between Mars and Jupiter. Most of the rocky material left over from the birth of the solar system, 4.5 billion years ago, never got the chance to become a planet. Instead, it settled into a wide, crowded ring of millions of asteroids, ranging from dust grains to bodies hundreds of kilometers across. Every so often, two of those asteroids collide. Most of the time it is minor, a chip here, a dent there. But occasionally, the collision is catastrophic enough to shatter a large asteroid completely, scattering a whole family of fragments across the belt. Astronomers can actually trace those families today, groups of asteroids that share almost identical orbits and compositions, all clearly descended from the same shattered parent. One of those families is called Eulalia, a group of dark, carbon-rich fragments that share a very specific, very interesting address in the asteroid belt. They sit close to what is called the 3-to-1 resonance with Jupiter, or J31 for short. Here is the simplest way to picture a resonance. Jupiter is so massive that its gravity does not just pull on nearby objects, it times them. At this particular distance from the Sun, any asteroid completes exactly 3 trips around the Sun for every single trip Jupiter makes. Get trapped in that rhythm, and Jupiter's gravity keeps tugging on you at the exact same point in your orbit, over and over, like someone pushing a swing at just the right moment every single time. Except instead of a gentle push, this repeated tug slowly stretches an asteroid's orbit into a long, elongated ellipse, one that eventually reaches far enough inward to cross paths with Mars, Earth, and the Moon. In other words, the 3-to-1 resonance with Jupiter is not just an orbital curiosity. It is a gateway. Fall into it, and sooner or later you are headed for the inner solar system. So researchers built a detailed model asking a simple question. What if the Eulalia parent body, a carbon-rich asteroid over 100 kilometers wide, broke apart right next to that gateway around 800 million years ago? Would the fragments actually funnel through the J31 resonance in large enough numbers, at roughly the right time, to explain what shows up on the moon? According to the simulations, the answer is yes, and the mechanism is more interesting than a single one-time explosion. About 3/4 of the shattered family's fragments eventually made it into the resonance, but they did not all arrive at once. Some were flung directly into the gateway by the sheer force of the original collision, an immediate injection straight into the danger zone. Others took a much slower path. They drifted for millions of years under the influence of something called the Yarkovsky effect, a subtle push caused by sunlight itself. An asteroid absorbs sunlight on its day side, heats up, and then re-radiates that heat back out later as it rotates. That tiny, constant imbalance between absorbing and re-emitting heat acts like an extremely slow, extremely patient thruster, nudging the asteroid's orbit a little further every single year. Given enough time, roughly 150 million years according to the model, that slow drift was enough to steer most of the remaining fragments straight into the same gravitational gateway. Either way, fast or slow, the ending was the same. Once a fragment crossed into the resonance, it was functionally on a one-way trip toward the Moon, Earth, and Mars. And this is where the story stops being a plausible idea and starts being something you can actually test. If you run the model forward and count up how many of those fragments should have struck the Moon and how big those craters should be, do the numbers match what is already sitting on the lunar surface? They do. The predicted impact rate and crater sizes line up with the ages already measured for Copernicus and its neighboring craters, including the same 800 million year timing that lunar samples had already been hinting at. That is the detail that turns this from a neat hypothesis into a genuinely convincing explanation. The model was not built to match the Moon's craters after the fact. It predicted them. Now here is where Earth comes back into the picture, and where the scale of this starts to feel enormous. The Moon is a small target. Earth is not. Because our planet is so much bigger, its gravity pulls in roughly 20 times more impactors than the Moon receives from the exact same source population. 20 times. That means for every single crater this asteroid shower carved into the Moon, something like 20 similar or larger impacts should have struck Earth over that same 150 million year stretch. Almost none of that would have survived in the rock record today. Remember, Earth erases its own scars within a few 100 million years, and 800 million years is more than enough time for weather, oceans, and tectonics to finish the job completely. So somewhere in Earth's deep, mostly unreadable past, there may have been a bombardment dozens of times larger than anything visible on the Moon today, and until this study, essentially no one was looking for it. Here is where the researchers get noticeably more careful with their language, and it is worth pausing on why. 800 million years ago also happens to be a strange, transitional period in Earth's biological history. Chemical signals locked into ancient rock, shifts in carbon isotope ratios, show real disruption around that time. Sections of the ancient ocean appear to have gone anoxic, meaning starved of oxygen, in patches. And in the fossil and molecular record, there are hints of a burst of diversification among marine eukaryotes, the broad group of organisms that would eventually give rise to complex multicellular life. On Mars, there is an echo of the same timing. The estimated ages of calderas on some of the planet's largest volcanoes cluster around that same 800 million year mark, hinting that the same wave of impacts might have jolted magma that was already sitting underground into motion. So does that mean a shattered asteroid, hundreds of millions of kilometers away in the belt, helped shape the chemistry of Earth's oceans and stirred up volcanoes on Mars. The researchers are explicit that they cannot say that, at least not yet. No direct physical evidence, like the telltale layer of iridium that marks the Chicxulub impact in rock layers worldwide, has been found linking this specific asteroid shower to those biological and volcanic changes. Ordinary cosmic dust, drifting in from unrelated sources, could account for at least some of the same chemical signals, and the authors say so plainly. What they have, in their own words, is a coincidence in timing striking enough to be worth chasing with more data, not a confirmed cause. That distinction matters. It is the difference between a headline that overpromises and a discovery that is honest about its own limits. And honestly, the honest version is still remarkable enough on its own. Because step back for a second and look at what has actually been demonstrated here, independent of the biology question entirely. A single asteroid, breaking apart in a specific spot in the belt at a specific moment in time, was enough to seed a bombardment that played out across 3 separate worlds, the Moon, Earth, and Mars, for more than 100 million years afterward. 1 collision, 3 worlds, 100 million years of consequences, arriving in slow motion, some fragments taking a direct hit and some drifting in on sunlight over millions of years, long after the original crash was already ancient history. That is the real headline of this research. Not that it proves what killed off one particular ocean ecosystem 800 million years ago, but that it shows, with hard numbers for the first time, exactly how a single catastrophe in the asteroid belt can ripple outward and quietly bombard an entire region of the solar system for eons. Confirming whether it also nudged the course of life on Earth and volcanism on Mars will take more of the same kind of careful dating and modeling that turned this from a coincidence into a testable hypothesis in the first place. Until then, the next time you look up at a clear night sky, or even just glance at the moon, it is worth remembering that some of what shaped this planet's history may still be hiding in plain sight, written into a world that never got the chance to erase its own scars.